All right. Well, thank you guys for joining me this morning, and happy Labor Day to you all. Um, let's see. And if you guys are watching later on YouTube or wherever, thanks for watching. Okay. Well, today what I will do is I will cover kind of the last section, which is section 5 in chapter 9. So we're going to wrap that up today. And that will be it for today. And then on Wednesday, I will have a review session at 10 a.m. All right, and that review session is optional. You don't have to attend. There's no viewing quiz associated with that. There is a viewing quiz associated with today's lecture, but there's none associated with Wednesdays. And then on Friday, we will have the final exam. Okay. I will also post after today's lecture. I'll post up some practice problems that you can work on to kind of help prep you for the final. So anyway, we'll get through the last lecture today. Maybe we can get through it a little bit quickly instead of taking up the full kind of 2 hours. I'll probably just try to power through it, no break today, and we'll probably get done hopefully a little bit quicker, and that will be it. That will be it for today. Okay, so like I said, chapter 9, part 2. Basically, the idea here is that we're going to we're going to continue on with hypothesis tests and confidence intervals, but in different situations. Before I go on, though, I just wanted to kind of highlight maybe just one of these problems, because yeah, I got some questions in my email about how certain problems should be carried out. So so this is one of the textbook problems. This is problem 9.36. And it says something like this. It says the weight of 4 randomly and independently selected bag of tomatoes labeled 5 pounds were found to be 5.1, 5.0, 5.3, and 5.1 pounds. Okay, so the idea here is, I don't know who buy. I don't think they sell tomatoes in 5-pound bags at this store. Maybe potatoes, but tomatoes, I'm not so sure. But anyway, this is in the land of math, when they make up problems, they have slightly strange setups. So anyway, here's bags of tomatoes, and apparently the label says this is a 5-pound bag, and we're going to weigh them and see if they really are 5 pounds now. And they come out to be a little bit different. So we're going to make a 95% confidence interval for the mean weight of all of the bags. And does the interval capture 5.0 pounds? So in order to answer this question, we need to calculate the mean and the standard deviation from our sample. And so this goes back to kind of chapter 3, when we were covering sample numeric summaries for samples. So our 4 values are these 4 numbers, and so the mean, the sample mean, x bar, is you just add those 4 numbers up and you divide by 4. So when you do that, you get 5.125. Okay, so you add up these 4 numbers, you divide by 4, and you get 5.125. And then to calculate the sample standard deviation, this is the formula that we use to calculate the standard deviation. So what we do is we take each number and subtract off the mean. So 5.1 minus the mean, 5.125, and we square that difference. We take each number and we take, what is its difference from the mean, and we square it. So or the deviation from the mean. So 5.0 minus 5.125 squared, 5.3 minus 5.125 squared, and 5.1 minus 5.125 squared. Okay, we take all of those things, we divide by n minus 1, so we divide by 3, and all of these numbers squared and added up, divided by 3, inside the square root, is something around 0.1258. So now we have the sample mean and the sample standard deviation. All right, if you wanted to, you could also use R to calculate the mean and the standard deviation. So you can just put the values inside a vector like so. X is this, you put the 4 numbers there, and you can just say what's the mean of X and what's the standard deviation of X, right? And so, you know, for the final exam, you are allowed to use any calculator you want, and you're even allowed to use R as a calculator to assist you in your calculations. So if you want to calculate the standard deviation of a set of numbers, you can just by typing in SD of X. I have no problem with that, okay? The other thing that we need when we're creating a confidence interval is you need to know the critical value T, okay? And so the critical value T, or the T star, comes from the T table. So what we have to do is we have to determine how many degrees of freedom we have and look up the confidence level. So the problem asked us to make a 95% confidence interval. And so for a 95% confidence interval, we have 4 values in our sample. So we have n-1, or 3 degrees of freedom. So the value I'm going to use for T star is going to be 3 degrees of freedom, 95% confidence. The value I use is 3.182. Right? And so at this point, it's just a matter of plugging in these numbers into the confidence interval formula, which is this: X bar plus or minus T star multiplied by S divided by the square root of n. You know, I will post a resource on CCLE with I've got a formula sheet that could be helpful for you guys. So let me, that's 10. Okay, so this I will share this document. Okay, now one thing to note is that there's one thing we did not cover. I skipped over in this class, and that's these confidence intervals, proportions, to samples. So basically, we've covered everything. There's kind of 8 little sections here, and we've covered 7 of them. We did not cover this one. You can put an X through that. But so anyway, when we are doing confidence intervals, means one sample. The interval is X bar plus or minus T times X bar plus or minus T times S, and where am I looking here? Okay, here it is. T times the standard error, and the standard error is S divided by the square root of n. So, and it talks about this. So I'll post this up. This is, I think, a helpful kind of summary sheet. And so anyway, this is what we have right here. The interval is this, and we just plug in the numbers that we have. So our mean X bar is 5.125. Our T star came from the table, and that's 3.182. My standard deviation is 0.1258, and my n is 4, and so I divide by the square root of n. And so when I do this, I get 5.125 plus or minus 0.2, and I get an interval of 4.925 to 5.325. And so our question was, well, we can say we're 95% confident that the mean weight of tomato bags is somewhere between 4.92 and 5.325 pounds. And the question was, do we have evidence that it's different from 5 pounds? Does the interval capture 5 pounds? Is there enough evidence to reject a mean weight of 5 pounds? So the interval does capture 5 pounds. 5 pounds is within the bounds of the interval, which means that we cannot, there's not enough evidence to reject a mean weight of 5 pounds. So it is possible that the mean weight of tomato bags is 5 pounds, and we can't reject that. So so that's the solution there. Okay. All right. Continuing on in the textbook, okay, is there's another problem, problem 9.4, and we are going to conduct a hypothesis test. Okay, and here it says use a two-sided alternative hypothesis. Should we be able to reject the null hypothesis that the population mean is 5 pounds using a significance level of 0.05, why or why not? Okay, and so here, before we even we don't actually have to based on the confidence interval alone, we can answer the question. So they gave us a slightly different confidence interval. They're just saying hypothetically, let's say the confidence interval is 4.9 to 5.3, which is slightly different from the confidence interval that we found. Okay, but that's fine. The question here is, based on this confidence interval, what can we say about the hypothesis test? And so a confidence interval and a two-sided hypothesis test should come to the same conclusion, all right? So when you do so if the confidence interval says that you should, that you have evidence that the mean is different from some value, then that means the corresponding hypothesis test will also come to that same conclusion, that you have evidence that the mean is different from some value. If the confidence interval says you do not have evidence that the mean is different, then your hypothesis test will also come to the same conclusion, that you do not have evidence that the mean is different. So those are things that you'd have to kind of keep in mind when you carry out a hypothesis test, is that it should align with the confidence interval. All right, so let's answer part A. Okay, and so so in our case, doing a 95% confidence interval will come to the same conclusion as a hypothesis test with a significance level of 0.05. All right, and then kind of going along with that, a 90% confidence interval will come to the same conclusion as a hypothesis test with alpha equal to 10%, and a 99% confidence interval will come to the same conclusion as a hypothesis test with alpha equal to 0.01. Okay, so it's kind of just like you add the 5% for the alpha and the 95% to get 100. Or if you have alpha is 10%, then it corresponds to the 90% because those two numbers add up to 100. Okay, so if our confidence interval goes from 4.9 to 5.3, that means we do not have evidence that the mean is different from 5 pounds, right? So can we reject the hypothesis that the mean is 5 pounds? So our confidence interval says we don't have evidence that it's different, so the corresponding hypothesis test would come to the same conclusion. So that means that the corresponding hypothesis test will result in a p-value that is greater than 0.05, right? So our confidence interval does not provide evidence that the mean is different from 5 pounds because 5 is between 4.9 and 5.3. And if we were to conduct a hypothesis test with alpha equal to 0.05, we would not find evidence that the mean is different from 5 pounds either. So that means we would not reject the null hypothesis. And if we were to go through the calculations and find the p-value, whatever it is, our p-value would be greater than 0.05. So we can come to a conclusion regarding our hypothesis test and our p-value just from observing a confidence interval alone. Are there any questions on this? Okay, then I will go ahead and conduct the second part of that question, which is carrying through the hypothesis test. Okay, so the hypotheses, when we write them, it's important to remember that they're always about the population parameters. So we would never use X bar, which is a sample mean, but we would always use mu, which is the mean of a population. The null hypothesis always has an equal sign, and in this problem, we have a two-sided test. So our alternative will have a not equal sign. Okay, and we know it's a two-sided test because the problem says use a two-sided alternative. Okay, but in other problems, based on how the question is written, you would use either a two-sided test or a one-sided test. And here we just kind of, if it's just a, do we have evidence that it's different from 5 pounds, that would be an indication of a two-sided test. If it says, do we have evidence that it's greater than 5 pounds, or do we have evidence that it's less than 5 pounds, then we would use a one-sided test. So our null and alternative hypothesis, when we write them out, will be this. The null is mu equals to 5, and the alternative is that mu does not equal 5. So we will use a significance level of alpha equal to 5%, and we'll also check the conditions to use the central limit theorem. Okay, and so it says, it told us that our sample of tomato bags was random and independent. So, or it said that we selected four bags of tomatoes that were labeled 5 pounds randomly. Okay. The problem tells us to assume normality. So if I believe that's what it says. Okay, so here it says assume normality. Okay, so back on this page, when if we assume normality, then a sample size, even though there's only 4 units in it, or even though there's only 4 observations in our sample, any sample is large enough if you assume normality. Now, if our sample was not normal, then we would have problems because a sample size of 4 is not going to be big enough. If your sample is not normal, then the rule of thumb is a sample of around 25, something around there should be big enough. Okay, the population would be it should actually be all bags of tomatoes, and I have to assume that there are more than 10 times 4, so more than 40 bags of tomatoes, and I think that would be that's a reasonable conclusion because there'd be a lot of tomatoes out there. All right, so we would go through and calculate the p-value, which is the probability of observing our data or something more unusual if the null hypothesis were true. So if the null hypothesis were true, we would expect any sample that we draw to have a mean of around 5 pounds. And what we observed was that we observed a sample where the mean, X bar, is 5.125, okay? So with a standard deviation of 0.1258. So how likely is a random sample to produce this kind of number, 5.125, if the mean is 5? Okay? So if the null hypothesis were true, we would expect random samples to have a mean of 5.0. We got something a little bit different. We got a sample mean of 5.125. So our p-value is what's the probability that a random sample has a mean that is 0.125, which is the difference between what I observed and what I expect if the null hypothesis were true. You know, what's the probability of getting a sample with that difference or something greater? So that means we want 5.125 and higher, and also 5 minus 0.125, so 4.875 or lower. So if the null hypothesis were true, then we can say the sampling distribution can be approximated with a normal distribution. However, because we are estimating the standard error, this is an estimate of the standard error. We don't actually have the population standard deviation. We will use the t-distribution for calculating our p-values. So X will be approximately normal with a mean of 5 and a standard error of 0.0629. Okay, but again, we're going to end up using the t-distribution. So our test statistic is the difference between what we got, 5.125, and what we expect under the null hypothesis, which is 5.0. 5.125 minus 5 divided by our standard error of 0.0629. That's going to give me a test statistic of 1.987. Okay, and we have 3 degrees of freedom. And so I will go to the table, and we're going to look up this number 1.987, and we see 1.987 for in the row 3 degrees of freedom. 1.987 fits in between these two columns, fits in between 1.638 and 2.353. Okay, so we look at the column headings, and we see that the corresponding right tail area, right tail probability, is going to be between 0.100 and 0.050. So that's going to be our tail area. And because our alternative hypothesis is two-sided, our total p-value is going to be 2 times our tail area. So if I double 0.1, I'm going to get 0.2, and if I double 0.05, I'm going to get 0.01. So whatever my p-value is, and I don't have an exact number, it's going to be between 0.2 and 0.1. And so if I know my p-value is between 0.2 and 0.1, I know I will not reject the null hypothesis because my alpha of 5%, if my alpha is 5%, I know my p-value is greater than alpha. Okay, so the question is, if you don't have if you have a degrees of freedom that's not on the table sheet, you just pick the degrees of freedom of the value closest to it. Kind of the general advice is to always round down, but if you're really close, you can just pick the one that's closest to it. So if you're at, like, say 79 degrees of freedom and you don't have 79 degrees of freedom, you can use 80 degrees of freedom. But the general advice is to always round down, which is a little bit more of a cautious move by rounding down. So if you can't find the exact degrees of freedom, they recommend you round down because it's a little bit more cautious. But if it's really close, if you can just use the one that's closest. But it's kind of the guideline. Let me give you the first quiz answer for today's viewing quiz. So the first quiz answer for today's viewing quiz is E as in elephant. E as in elephant is the answer to our first viewing quiz today. Okay, so this is just the conclusion. If the p-value you get is between 0.2 and 0.1, we will not reject the null because our p-value is greater than the null. And so we say we do not have evidence that the mean is different from 5 pounds. If the true mean is equal to 5 pounds, we would expect random samples also to have a mean of 5 pounds. And even though our sample has a mean of 5.125 pounds, this is not an unusual result. All right, so hopefully this is a good example that kind of helps make you feel a little bit more comfortable with doing t-tests. And this is all stuff that we covered last week in lecture, but I know using the table can feel a little awkward and strange. So I hope, with practice, the t-table is okay. So we have a question. It says, what if the range of the p-value is partly greater than and partly less than the significance level? What would happen? So based on the way the t-table is constructed, as long as you're using, quote, reasonable p-values or reasonable alpha levels, then this won't happen. So if you use an alpha of 5%, then if you have a one-sided test, you will either be greater than or less than 5%. If you have a two-sided test, you can kind of look at this number, 0.025, and you'll either be greater than or less than. The only time you would run into this problem where you have the range of the p-values partly greater than or partly less than the significance level is if you decide to do something like a 7% significance level. Okay, now if you had a 7% significance level and you end up between 0.05 and 0.1, then you're right. We would not be able to answer that question. And so if you choose something like a 7% significance level, then you would need to go to the computer to get a more precise p-value to be able to answer your question. But if you're picking alphas like 10%, 5%, 1%, those will all be listed in the table, because for 1% you can, on a one-sided test, you can just look at this number, or for a two-sided test, you would basically look at this number, and after it gets doubled, it becomes 1%. And for 5%, you know, either this or this, or 10% this or this. So if you're using 1%, 5%, 10%, which are probably the most common choices for alpha, then the t-table will be fine. But yeah, if you pick something a little strange like 4% alpha or 7% alpha, then yeah, you would not be able to use the table. Okay. So if you want to use R rather than the table, this is also an option. So so this is what you could do is, you know, after you go through your calculations and you get your test statistic of 1.987, you can throw that into R and type in PT, and PT would tell you the area to the left of 1.987. And so what we want is we want the tail area, and we want 2 times the tail area. So to get the tail area, we can do 1 minus PT. You could also do PT of negative 1.987. That would also work, but 1 minus PT will give us something around 7%, 0.0705. And because we have a two-sided alternative, we would double that, and it would do 2 times 0.0705. And we would get a p-value of around 14%. Okay, and so even though when we use the table we didn't get an exact value, the table said our p-value is going to be between 10% and 20%, 0.2 and 0.1, which aligns with what we found, which says our kind of a more precise p-value is around 14%. Okay, and so again, if you need more precision, you'll have to go to R rather than using the table. Okay, but again, with alpha equal to 5%, we would not reject the null hypothesis. All right, so the last section in the textbook that we'll cover is section 9.5, and that is comparing 2 population means. And so the idea here is that we're going to have 2 samples, and we want to compare those 2 samples using a t-test. Okay, and there's actually 2 scenarios that we want to consider. There are samples where there's a scenario where the samples that we are comparing are independent of each other, which means that the measurements you take for one sample are unrelated to the measurements that you take for another sample. All right, and then there's also paired or dependent samples where the measurements in one sample are all related. Okay, every measurement in this sample is related to a measurement in the other sample. So I'll give you some examples of each of these things. And for these things, we'll make a confidence interval and perform hypothesis tests. So let's start off with the independent samples. Okay, so let's do some examples to distinguish between independent and dependent samples, I should say. So we're going to so here's an example where it says we select a sample of randomly selected adults from the United States are asked to rate the taste of a new soft drink. So we say, here's this new drink. Tell me how much you like it on a scale of 0 to 10, right? And then they also go to, they select some adults from Britain, the UK, and they also ask them to rate the taste of the soft drink on a scale of 1 to 10, right? So it's a known thing that people from different countries have different kind of taste preferences. And so depending on where you go in the world, they might change the formula of a soft drink to kind of appeal to, that population. So we want to know, is there a difference in the score here? Okay. So in this case, the two samples that we've selected, the adults that we've selected in the United States and the adults we've selected from the United Kingdom are not related to each other. So these two samples are independent. Okay. Here's another scenario that's similar, but in this case, we would get dependent samples. So here we have a sample of randomly selected adults, and we give each adult two soft drinks. We give them drink A and drink B, and we ask this adult to rate drink A, and we ask the same adult to rate drink B. And we want to compare the scores between drink A and drink B. So it's a similar scenario, but here, the same adult is providing the score for drink A and the score for drink B. So the two scores that we get, the score for drink A and the score for drink B, are generated or come from the same person. And therefore, each score that we have for drink A can be paired with a score for drink B. We can say this is the drink A score from Bob, and this is the drink B score from Bob. This is the drink A score from Alice, and this is the drink B score from Alice. So every score can be in one group can be paired with the other group, and so we have to treat this as paired data or dependent data. Okay, because let's say Alice just kind of hates soft drinks in general, so she's going to give a low score to drink A and a low score to drink B. Maybe she likes drink B a tiny bit more than drink A, or she hates drink B less than she hates drink A. But it might be like a score of 1 and 2 for each of these things. And maybe Bob loves all soft drinks, and maybe he has a slight preference for drink B over drink A or something, and he might give it a score of a 9 and 10 or something like that. But we want to kind of take into account all of these individual preferences overall. Whereas in the first example, when we're dealing with scores from the US and the UK, those people are completely unrelated, and there's no reasoning behind, like if you were trying to pair them, there's no reasoning or no real logical or reasonable way to do it. Okay. Another telltale sign that you have independent data is that if you have two samples and the sample sizes are different, then they absolutely have to be independent. Okay, so if you have one sample has 20 people and another sample has 22 people, then they cannot be paired because there's no way to match up all the observations in one sample to an observation in the other sample. Okay, if they're paired, they have to have the same number of observations in both samples. Okay, but just because they have the same number of observations does not necessarily mean that they're paired. But having different number of observations absolutely means they must be independent. All right, so when you deal with independent samples, what we're doing is we're looking at two samples of data, and the question that we want to know or that we want to answer is, do the respective populations, right? So if we assume this sample came from one population and this sample came from another population, right? So in our example, we took a sample of adults from America, and so the respective population would be all adults in America, and the other sample were adults from the UK, and the population there would be all the adults in the UK. So we have respective populations, and the question is, do the respective populations have different means? So this is kind of a little diagram that I've set up. So the idea is there's a big population. This is population 1 with mean mu1. And from population 1, we select a small sample. That's this little circle. Population 2 has mean mu2, and we select a small sample there. And so we get sample 1 and we have sample 2. And the issue is that we only get to observe sample 1 and sample 2. So from sample 1, we can observe the mean, x bar 1, and the standard deviation, and the size. So we have S1 and N1. And from sample 2, we also get the mean, standard deviation, size. So we have x bar 2, S2, and N2. All right, so we only get to see the values here. And based on this, we want to know, we want to infer back to the populations and ask, do the populations have, do we have evidence that the populations have different means, or could the populations have the same mean? And the proper way to do this is not to look at one sample and make a conclusion about population mean 1, and not to look at sample 2 and look at population 2 separately, but rather to look at the difference between the means. So we're going to look at x bar 1 and x bar 2, and we're going to ask, what can we say about the quantity mu1 minus mu2, which is the difference between the mean of population 1 and the mean of population 2. Okay, so this is what we want to answer. This is the question that we want to answer. What can we say about the quantity mu1 minus mu2? And that quantity represents the difference between the population means. And so if the null hypothesis are not, well, before I even get to the null hypothesis, the question that we really want to know is, could this difference equal 0, right? If mu1 minus mu2 could equal 0, then that means the two populations could have the same mean, because if mu1 minus mu2 is 0, that happens when the two means are equal to 0. So if it could equal 0, so if our conclusions say, yeah, it could be 0, then the two populations could have the same mean. Okay, on the other hand, we might have evidence that mu1 minus mu2, that this quantity is not equal to 0. And if that's the case, then we have evidence that the two populations have different means. So if we have evidence that mu1 is not equal to mu2, mu1 minus mu2 is not equal to 0, then we have evidence that the two populations have different means. So effectively, this quantity is the parameter that we want to estimate, okay? So it looks like it's mu1 minus mu2, but we can also just think of this as just the quantity that represents the difference, okay? And we're not going to be able to get an exact value for this because we don't have direct access to the population. But like before, we can create a confidence interval for this quantity, mu1 minus mu2. We can also perform a hypothesis test for it. So if we want to make a confidence interval, it could look something like this, right? So for example, let's say we have two independent samples. One is a sample of adult men, and another sample is a sample of adult women, and we measure their heights. And if we make a 95% confidence interval for that difference, mu1 minus mu2, the resulting confidence interval might go somewhere from 4 inches to 8 inches, so something around there. Okay, and we would just say, I'm 95% confident that the average height of adult men is somewhere between 4 and 8 inches taller than the average height of adult women. This is not saying anything about an individual man's height or an individual woman's height, or it's not also saying anything about the mean height of all men and the mean height of all women. It's just saying the difference, as far as the difference between the average height of men and the difference and the average height of women, as far as that difference goes, it's likely to be somewhere between 4 and 8 inches taller. All right. So it's important to note that the confidence interval does not say anything about the average height of men alone, which is something around 69, 70 inches, or the average height of women alone, which is something around 64 inches. It's a statement about the difference. And so because 0 is not inside our interval goes from 4 to 8 inches. So 0 is not between the ends of the interval. That is, our interval goes from 4 to 8. We have evidence that the difference between population means is not 0. And so that means we have evidence that there is a difference between population means. Okay. On the other hand, if we have a confidence interval that includes the value 0, then we would say we don't have evidence that there's a difference. So the formula for making a confidence interval to compare two population means, this is just the formula. X bar 1 minus X bar 2 plus or minus T times this. Okay, this thing here represents our standard error. Okay, so the estimated standard error is S1 squared over N1 plus S2 squared over N2. And the margin of error is T star multiplied by our standard error. Okay, and again, I've put all of this in our formula sheet. Okay, so the interval is X bar 1 minus X bar 2 plus or minus T star times the standard error. And the standard error is given by this formula. Okay, so it's just a matter of plugging in numbers. So the formula has changed, but the logic regarding the confidence interval has not. That remains the same. So we're going to look up the value in the T table to get our critical value, T star. And the truth is that the actual degrees of freedom, when you have two independent samples, the actual degrees of freedom is kind of a complicated matter. And so the approximation is to use n minus 1. And we have two n's, and so we're going to just use the smaller of n1 and n2. The question says, is it possible that we would be given sigma and then we would have to use z star instead of t star for these confidence intervals? I mean, I will not do that. I would not do that on an exam. And, I guess in some hypothetical situation it's possible. But I would say in general, in real life, it's very, very, very unusual to have a situation where you would have sigma but not mu. So, because that would mean you know the population standard deviation, but you don't know the mean of the population, which is a little bit strange to think about. Okay, so so generally, if you don't know the mean of the population, you probably don't know the standard deviation of the population. But hypothetically, if you were in that scenario, yes, you would use z rather than t if you knew the mean of if you knew the standard deviation of the population. Okay, but I can't think of real life scenarios where that's the case, and I would not put something like that on the test either. All right, so anyway, what we're gonna do here is that we just use n minus 1 degrees of freedom, and we have two values for n. We have an n1 and an n2, and so we're gonna just use the smaller of n1 and n2. So whichever n is smaller, that's the one we're gonna use for n minus 1. So here's just a silly example, and I don't know if this is even legal, but apparently you have people applying for a job, and they're going to give you a skill test, and they're going to count how many blocks can fit into matching holes in a 1 minute period, right? And so they collect data on a random sample of 20 young adults and 15 senior citizens, and we're going to assume normality, and And we're going to say the average number of blocks that the young adults are able to do is going to be 28.2 with a standard deviation of 4.3. And the average number of blocks that the seniors were able to do within that 1 minute period was 24.3 with a standard deviation of 5.7. So we want to know, okay, you know, we got an average of 24.3 and an average of 28.2 in our samples. Does that mean that the populations have different means? So we're going to make a 95% confidence interval for the difference between means. Does the confidence interval provide evidence that there's a difference in the average number of blocks completed by young adults and seniors? So if this is what we observe in our samples, does that mean that the populations have different means? So that's what we want to do. Okay, so we're going to compare 28.2 and 24.3, ask what it says about the populations. So I'm going to just plug these into the formula. So just to kind of summarize the values from the problem, the X bar 1, S1, and N1 are 28.2, 4.3, and 20. And then we have 24.2, 5.7, and 15 for the seniors. Okay. So when we look up the T star, we have N minus 1 degrees of freedom. So we're going to look at N1 and N2. We take the smaller sample, 15, and we do 15 minus 1. We're going to use 14 degrees of freedom. So if I go to the T table and I say, all right, we've got 14 degrees of freedom, 95% confidence at 14 degrees of freedom. The number I use is 2.145. So at 2.145, I'm going to plug that in to T star. And then here, you know, once I've listed off all the problems from the values from the problem, it's just a matter of matching them up and plugging them in. So I get 28.2 minus 24.3 plus or minus 2.145, plug in the numbers for the standard error, okay? And so this you have to compute out. So the observed difference between my two sample means is there's a difference of 3.9 plus or minus my T star is 2.145 and my standard error is 1.758. And so I get 3.9 plus or minus 3.77, which ends up being between 0.13 and 0.767. So I would say I'm 95% confident that on average, young adults can complete somewhere between 0.13 and 7.67 blocks more than seniors on average. All right, and so because 0 is not within the bounds of our interval, so my entire interval is above 0, we do have evidence that there is a difference in the average number of blocks completed by the two groups in the population. Okay, so we have evidence that the means of the population means are different. If this interval went from, say, -1 to +6, okay, then 0 would be in between -1 and +6, and I would not have evidence that there's a difference because 0 is in there. So the question is, could 0 be the value for mu1 minus mu2? And here we have evidence that 0 could not be the value. All right, I hope that's okay. The flip side, so here I've arbitrarily chose the young adults to be labeled to be sample 1 and seniors to be sample 2, okay? And so what if I swapped them? What if we called seniors sample 1, so we had X bar 1, S1, and N1 over here, and the young adults were sample 2, and so this is X2, S2, and N2, okay? So what would happen is that I would kind of swap the labels of X1 and X2, right? And I would get 24.3 minus 28.2, but everything else would remain the same because T star would still be 2.145, and my standard error, okay, I would swap the because they're just being added inside the square root. You know, I'm just kind of swapping the positions of these kind of these fractions here, and so it's not going to affect the size of the standard error. So the only thing that changes is that this number which used to be 28.2 minus 24.3 and gave me positive 3.9, becomes 24.3 minus 28.2 and becomes negative 3.9, okay? So swapping the labels of which one is group 1 and which one's group 2, the only thing that changes is that this becomes negative, but everything else from is the same. So I get negative 3.9 plus or minus 3.77, and my confidence interval ends up going from negative 0.767 to negative 0.013. And so the conclusion here, now that they're negatives, would be that I'm 95% confident that on average seniors complete between 0.13 and 7.67 fewer blocks than young adults on average. So the conclusion on the previous page was I'm confident that young adults complete between 0.13 and 0.7 and 7.67 more than seniors. And here I'm confident that seniors complete between 0.13 and 7.67 less than the young adults. So it's the same thing, just from a different perspective. One is we're saying group A does more than group B, and the other we're saying group B does less than group A, right? So it has the same meaning, it's just our point of reference has changed. And again, because 0 is not in the interval, we come to the same conclusion that we do have evidence that there is a difference between the average number of blocks completed by the two groups. Okay, I hope that's all right. So I kind of went through this a little bit quickly, but this is a confidence interval, and I hope, because we've seen a bunch of confidence intervals already. We've seen confidence intervals for proportions and confidence intervals for means. I'm hoping that the confidence interval for difference is not a huge leap, okay? And it's just because we're looking at the difference, the question that we're going to always kind of be coming down to is, could that difference be 0? All right, so the next part is we're going to do a hypothesis test. I'm going to go ahead and use the exact same data to make a hypothesis test. And so here's the data. I've got all the values labeled. And we want to know, is there evidence that there's a difference in the average number of blocks completed by young adults and seniors? All right, so we already know that the conclusion is going to be yes, right? Because here the confidence interval came to the conclusion that we do have evidence. And so when we do the hypothesis test, we should come to the same conclusion that we do have evidence of a difference. But I'm going to go ahead and go through the steps of the hypothesis test so that we have kind of an example of how this works. All right, and so step one is to make the hypotheses. And again, just like before, hypotheses are always about the parameters mu, never about x bar. And the null hypothesis always has an equal sign. So when I set up my hypothesis, the null hypothesis is that mu1 is equal to mu2. Okay? I could also write the difference mu1 minus mu2 is equal to 0. That would also be equivalent. Right? And then the alternative is that mu1 is not equal to mu2. So we have a two-sided test because we're just asking for a difference here. It's possible that we could have asked the question that, do we have evidence that young adults do more blocks than seniors? That's also a possible question. But here we're going to just say mu1 is equal to mu2 and mu1 does not equal mu2. Those are the null and alternative. So we're going to start, say our significance level, alpha is 5%. We'll go ahead and check the conditions to use the central limit theorem. So it said the samples were randomly selected. So we'll say that condition is met. It also tells us that to assume normality. So this condition is also met. If it did not say assume normality, then the large sample condition might not be met because we have samples of 15 and 20, which is not quite big enough. So the big enough sample is usually around 25 if you're not sure if it's normal or not. And then the big population would be kind of all the young adults and seniors that might apply for the jobs. And so as long as, you know, over 200 people, young adults, and over 150 seniors kind of apply for jobs at this company, then the population would be big enough. But it's also possible that it's not. So these are just things to kind of keep in mind. All right, so we'll go ahead and compute the p-value, which is, you know, the probability of observing our data or something more unusual if the null hypothesis were true. So if it were true, then we would expect the two random samples to have the same mean, or that there to be a difference of 0 between the two means. Okay, and in our data, our two samples don't have the same mean. One is 28.2 and the other is 24.3, or there's a difference. We observe a difference of 3.9. And the question is could this difference of 3.9 have been the result of randomness? And so specifically, the p-value is what is the probability that two random samples will have means where the difference is 3.9 or more. All right, so again, our standard error is given by this formula, S1 squared over N1 plus S2 squared over N2, which we've estimated to be 1.758. And our test statistic, which I've kind of written out in words in this huge thing, will be the observed difference between sample means minus the expected difference if the null hypothesis were true. So what we observed was the difference of 3.9, or x bar 1 minus x bar 2. That's the observed difference. And if the null hypothesis were true, we would expect a difference of 0. And whenever you take two random samples, you would expect the two random samples to have a difference of 0. So my t is going to be, you know, basically 3.9 minus 0, or I can just leave that off, 3.9 divided by my standard error of 1.758. So I get a test statistic of 2.218, and I'm going to look this up in the table using n minus 1, or 14 degrees of freedom. So again, I've got two n's. I've got n1 is 20 and n2 is 15. And so using the smaller between 20 and 15, we're going to say, okay, 15 minus 1, 14 degrees of freedom. So this is my test statistic, 2.218. And we go to our table, looking at the table for 14 degrees of freedom. I look up 2.218, which is in between these two columns, in between the columns for 0.01 and 0.025. So I know that my tail area, whatever it is, I don't have an exact value, but I do know my tail area is between 0.01 and 0.025. And my alternative is two-sided, so I'm going to double this. So I don't have an exact p-value, but I do know my p-value is between 0.05 and 0.02. Okay, so I know it's less than 0.05 and I know it's more than 0.02. I don't know exactly what it is, but I do know it's less than 0.05 and more than 0.02. And so because I know my p-value is less than 5%, I will be able to reject the null hypothesis. Okay, so even though I don't know the exact value, I do know that it's less than 5%. So that means I will reject the null hypothesis, and I have evidence that there is a difference between the population means. So if the two populations do have the same mean, we would, you know, when we take random samples, we expect them to have the same mean. We had a sample of a difference of 3.9, which it would be considered unusual and unlikely to happen by random chance alone. And so the fact that we did get a sample, two samples where the difference is 3.9, provides evidence that the null hypothesis is wrong, that the populations have different means. All right, how do we feel about all of this? I hope okay. Let me give you your second quiz answer, viewing quiz answer. Second quiz answer is B as in bear. That is the second viewing quiz answer, is B as in bear. Okay, well, thank you for saying you feel good about this. Okay. All right, and I'm gonna go ahead and just kind of power through rather than take a break. I just have a kind of one little last thing to cover, and then we'll let you out early. It is Labor Day after all, and so thanks for joining me anyway. And so we'll cover the last section, and I think that'll be it. Okay, so the last one is comparing means of paired samples. All right, and this is rather quick, okay, because comparing means of paired samples actually is basically the same as doing a hypothesis test for one sample, but well, let me explain. Okay, so sometimes we'll collect measurements that are related to each other. So common examples are before and after studies, or couple or twin studies, or you'll just have matched pairs. So you might have a study where you took like measurements before something and then measurements after something. So you said like, what is your, I don't know, your blood pressure at the start of this thing, and then we have you exercise for every day for 6 weeks, and we say, well, did that lower your blood pressure? And we take an after measurement. Okay, or you could ask couples, people in relationships, and you ask person one, you know, how do you feel about this? And you ask their partner, how do you feel about this? Okay, or you have twins, and you ask, you know, one person, you know, you take some measurement on this, and you take a measurement on the other person of the twin study. Okay, or you might have matched pairs where maybe you have two different groups, but you kind of line up all the measurements based on kind of demographics and stuff. So you might say like, okay, we have, you know, a sample of students from this school and a sample of students from this school. And we tried to line them up. We tried to line up, you know, this student's score is going to be compared to this student's score because, you know, based on other demographic things, right? Maybe they're the same age and same ethnicity and same socioeconomic status or something. You're going to try to match up the two you try to match up every observation in this group with a observation with someone else. Okay, so that would be a matched pairs study. And so the key idea here is that every measurement that we've taken in one group is matched to a measurement in the other group, right? So with paired studies, you don't actually care about the individual measurements. You only care about the difference between the two the matched values. So when you take the matched values, we only care about the difference. We don't actually care what this value is and this value. We don't care what the before and the after. We just care about the change. So if you have a before and after, we only care about the change. We don't. So maybe it's you're interested in, I don't know, some kind of weight loss thing. We don't care about the before weight or the after weight. We only care, is there a difference? Is there a change? So here, this is, I think, an example from the textbook, which is a little strange, which is there a difference in a person's ability to smell when they are sitting versus lying down? This is not a question that I've ever asked, but now that this was presented to me, I was like, trying to smell sitting versus lying down. Never even thought of smelling things lying down, but anyway, so I guess we took 4 people. We gave them a smelling test when they were sitting and a smelling test when they were lying down. And I don't know exactly what a smelling test looks like and how you get numbers out of it, but this is what we have. And so sitting, person 1 scored a 13.5, and lying down, the person scored a 13.25, and person 2 scored this, and lying down they scored this, and so on and so forth. And so we have, so the same person is scored both on sitting and lying down. So it's not that we took 4 people and gave them sitting scores, and we took 4 different people and gave them lying down scores. We have the same person producing the sitting and the lying down score. And so what we have to do for this kind of analysis is that you create a new column. We're going to add a 3rd column for the difference. You're just going to do one column minus the other. So we're going to subtract the lying down score from the sitting score, and we're going to get the difference. So 13.5 minus 13.25, we get a difference of 0.25, a difference of 0.5. Here we get a difference of 1.25, and this person had the same score, so we have a difference of 0. Okay, and so now that we've calculated this difference column, this becomes the only column that matters. Okay, the only column that matters. So just kind of like the problem that we saw at the very beginning, this reduces down to one sample, and I've got 4 values, and you have to calculate the mean and the standard deviation. And so I've kind of skipped over the individual steps of calculating the mean and the standard deviation. The mean of these values, if you compute it, the mean is 0.5, and the standard deviation, if you compute it, is 0.54. Okay, and again, I've skipped that, but I figure you guys know how to do this because we saw an example of this when we were dealing with the bags of tomatoes. Okay, so we have just, so we treat this as if it's one sample. You calculate the mean and the standard deviation of that one sample. Okay, and you know, in some problem, they might also give you the mean and the standard deviation of the sitting down scores and the mean and standard deviation of the lying down scores. Those are just there to distract you. Just ignore them, okay? They no longer matter. Once you calculated the difference column, that's the only column that matters. These columns no longer matter. Once you get the difference, that's it, okay? All right, and then, so now that you only have the difference column, then it becomes just a problem of one sample. So when you do the confidence interval for one sample, it becomes this, and we're going to just plug in the values, okay? So on the formula sheet, I don't have, I didn't create a confidence interval for, so when it says 2 samples, this is for 2 independent samples. Confidence interval 2 samples, it's for 2 independent samples. Because when you have confidence intervals for paired samples, it reduces down to basically confidence interval of 1 sample and a hypothesis test of 1 sample. Okay, so this is a confidence interval for 1 sample, and again, we only have just this one column of values. So I'm going to plug in 0.5 plus or minus. I look in 3 degrees of freedom, 95% confidence, 3.182, standard error of 0.54 divided by the square root of 4. So my confidence interval goes from negative 0.36 to 1.36. And the question is, could the difference be 0? Okay. And so because 0 is between the interval, right? The answer to this question, is there enough evidence to say that there's a difference between sitting scores and lying down scores? The answer to that question is no. Okay, the interval contains 0, so it is plausible that the mean difference is 0, meaning that it is plausible that there's no difference between the mean score for sitting and lying down. So our conclusion, based on our data, is that we do not have evidence that there is a difference. So again, we treat this as if it's one sample, but then the question is, could the mean of the sample be 0? And here the mean of the sample could be 0, so we do not have evidence that it's different from 0. Okay, if we want to do a hypothesis test, we kind of follow the exact same steps, and I think at this point, you guys, I hope, I don't know, maybe not. I'm going to just kind of go through it quickly, right? So the hypotheses here, right, is that the mean, the difference is 0 versus it's not 0. That the mean difference is 0 versus it's not 0. And again, we can check all of our conditions here. We have 4 people, and we're going to assume that they're random and independent. The problem didn't specify to assume normality, so we kind of just have to assume that it's okay. If it's not normal, then we could run into problems, okay? So we have a sample. Again, once you've reduced it down to that column of differences, That's the only sample that matters. So we have 4 people in that sample. We have an observed mean of 0.5, a standard deviation of 0.54. Okay. If the null hypothesis were true, mu would equal to 0, and we would expect the difference to be 0. And our sample has a difference of 0.5. So, and again, the important thing is that we're just talking of the mean of the difference column and not the difference between the mean sitting score and the mean lying down score. Okay, so again, I guess if students were to make a mistake here, a common mistake is to treat the 2 samples as independent when you have to treat them as paired and you're only dealing with the difference column. So again, just like the calculations for 1 sample, we're going to do x bar minus mu divided by the standard error. So my standard error is s over the square root of n. I get a standard root of 0.27. Here my t is 0.5 minus 0 divided by 0.27. I get a test statistic of 1.852, and we have 3 degrees of freedom. So I go to the table with 3 degrees of freedom. 1.852 is between here and here. And so my corresponding tail area is between 0.1 and 0.05. And therefore, when I double it, because my alternative is 2-sided, I'm going to get a p-value between 0.2 and 0.1, which means we do not reject the null hypothesis. Okay, so we don't know what the exact p-value is, but we know it's more than 5%. So we don't reject the null, and we have no reason to suspect that sitting or lying down makes a difference in smelling ability, which is the same conclusion that we came to when we did the confidence interval. The confidence interval had 0 between the ends of the interval, so we had no evidence of a difference. When we carry out the hypothesis test, we come to the same conclusion that we don't have evidence that sitting or lying down makes a difference in smelling ability. Okay, I hope that's okay. That's it for today. I'll give you your final viewing quiz answer, which is also B as in bear. Okay, so your last quiz answer for the day is B as in bear. And that's it. I don't know. Are there any questions? Okay, so we have, all right, so someone has a private question. Okay, after class, that's fine. So after recording and everyone else signs out, I'll stick around. Okay, have a question regarding how the Gradescope quizzes are graded. All right, yeah, if you have questions about that, you can stick around after class. Okay, all right, well, that's it then. So we'll call it a day here. I'll post up some practice problems for you guys to work on, and that's it. Good luck as you guys study. And again, there's an optional review session on Wednesday, and so we'll see that. Will the last office hours be on Wednesday review session? Yeah, pretty much that's it. Okay, have a good day. Oh, if I could ask you a favor, fill out your course evaluations. I hope you've enjoyed the course, and if so, please fill out your course evaluations. And good luck as you guys study, and we will see you on Wednesday. And if not on Wednesday, then definitely on Friday. Okay, so I'm going to go ahead and stop